So this is X, Y, but I'm going to draw a cross section. This is a side view. C and Y, this is a cross section. What we do like before is consider a small element on the beam, just blow it up, draw a big figure for it. C, D, C prime, D prime. Now, given that this section is loaded, there's no reason to not believe that there won't be any stresses, normal stresses. So let's assume that the stress on face C prime is sigma C and it's sigma D. Okay. Okay, so then the net difference in the stress, normal stress, leads to a shear force, which is going to be resisted by delta H. Okay, so when I draw this, I'm actually drawing a cross section. And let's assume that the bottom surface of this C prime D prime is a distance of y1 from the neutral axis. This is the neutral axis. Okay, and then this is the top of the beam of the section. Let's call that C. So I can also draw a cross section like I drew earlier. Say that the width of this section is B. And this is y1 like before. Okay, we're going to consider some element at a distance of y, and let's say that that is dA. So delta H is the force on C prime D prime. And if we do a net equilibrium of forces in the x direction, we have delta H, you can see it's on the right side. We have sigma C times delta A. So converting stresses into forces, we require to multiply it with the cross-sectional area. And then there's dA, sigma D dA acting on the other side, so negative, should all be equal to 0. So we can write delta H is sigma D minus sigma C integral dA, just moving things around. But we know, but we know that sigma is m y divided by I. So this is something which we derived earlier. So we can just sub this in here. So we have delta H is integral md for the moment at D, y divided by A minus mc y divided by I times dA. You just copy it from the previous page. Okay, so what we are talking about is this C prime D prime. Okay, I'm just going to draw a 3D figure for this. Remember there's a delta H here. the way we've drawn this is a certain width b, and this element here is actually a length of dx. So what we can do is we can write delta H is, it's basically a force. It's going to be the shear stress, because the shear stress is something which is going to resist shearing. C prime D prime is actually shearing of the beam when the stresses are large enough, times the cross section area, but the cross section area is the area of this face. So that face is B times dx. Okay, so with that, I can now sub in, let's call this 1, call this 2, substitute 2 in 1, tau p dx is, I'm just going to assume that since that element is very small, there's moment md here, mc here. This element is so small that this difference md minus mc can be replaced with the change in moment. So I'm going to write this as dm y I dA with the integral. So what I can do is I can pull out dm, that's going to be constant, I divided by y d. So the same expression, except that md minus mc has been written as dm. Okay, we're almost there. Okay, I'm going to move things around. This b dx, I'm going to divide by b dx. So we have tau equals 1 divided by I dm dx integral y dA. We're getting a b. So I times, okay, that's better. So the b came down. But this is something we wrote down sometime back when we were doing shear force bending moment diagram. Dm dx, the rate of change of moment is nothing but the shear force V. CBMD SFD notes. Okay, so we have the formula is tau equals V for dm dx I B, and in this part integral y dA, I'll write it as Q, where Q is integral y dA. That's the, so to say, the famous shear stress formula for a beam. The shear stress is proportional to the shear force V. There's Q. Q is basically YDA, and then we have IB. Okay, now a little bit about this Q. This Q is important. In particular, how is this? How do you really compute this integral? Okay, so this is how you compute this integral, which is needed for any problem involving shear stress. In the neutral axis, this is the shear element at a distance of y1. This is the top, C. Okay, so we wrote tau equals PQ divided by I times B. Q here is actually integral from y1 to C y dA. Okay, so two cases. One on the neutral axis. So if you're going to from the neutral axis, y1 will be 0, then you can compute q as 0 to c y dA. Okay, now integral from 0 to c y dA is not equal to 0. You have to actually do the computation. Okay, so this is going to be, it's not 0. In fact, it is going to achieve a maximum value because that integral doesn't pass through neutral axis. Everything in that integral is positive. So tau is max at neutral axis. Okay. The second case is on the top edge. Here y1 would be c, right? This is the top edge. So here q would be 0. So sorry, y1 would be c, bottom limit. Top limit is c, y dA, that's 0. So tau is 0 on the top edge. In other words, the shear stress is 0 at the top edge. It's maximum at the neutral axis. This is exactly reverse of what you see for a beam, right? And that is actually one of the most important points. This is a very common way people make a blunder in the exam. They just compute the maximum, they assume that the maximum shear stress occurs at the place where the maximum normal stress occurs, and that's not true. Maximum shear stress occurs in the middle of the beam, while the maximum normal stress occurs at the top or the bottom of the beam. Rectangular, circular, hollow circular, and an I-beam, and it basically tells you the value for the maximum stress here.